Let's get this shared and pulled up. All right, and hello. Welcome to another fun installment of me rambling about linear algebra. So we're going to go through a couple problems, talk about some concepts of space, spaces, subspaces, and vectors. So let's get right into it. So our first problem, as we can see, hopefully you can see, the vector space R2, so the second dimension, is not a subspace of R3 in the third dimension because R2 is not even a subset of R3. The vectors in R3 all have 3 entries, whereas the vectors in R2 have only 2. The set H, which is equal to the vector of ST0, where S and T are real numbers, or just real in general, is a subset of R3 that looks and acts like R2, although it's logically distinct from R2. And we can see in our nice little figure here that this vector ST0 exists in a three-dimensional plane, and well, in 3 dimensions, and it forms a plane, happening to pass through the origin. So what does this really mean? And the main thing to kind of first get into is this idea of R2 versus R3. And that's a real interesting distinction to make between if this was, say, a vector in R2 consisting of just S and T. What does it mean to say it's not a subspace? Well, to say it's not a subspace of R3, you can actually go to some of the fun examples I pulled up or reference material. To be a subspace, you have to meet 3 criteria. The first of which is it has to contain the 0 vector, which means it has to go through the origin. Additionally, H is closed under vector addition. That means for any vectors u and v in H, the sum of u plus v is in H, and it's closed under scalar multiplication, which means that for any vector u within H, each scalar c, the vector cu is also in H. But the real kind of tricky and conceptually interesting bit is this 0 vector component. So if we pop back to this example here, I can see that at some point, S and T being real, there's going to be a point where it's all going to be 0. It's going to hit right here at the origin. The trippy bit with the 2Ds, there's not a good way to map it into 3D, because when we say that ST0 looks and acts like R2, is this forms a 2-dimensional plane. But this order is more or less arbitrary because S and T would exist in R2. However, there's nothing that really denotes or implies or actually forces us beyond just making an arbitrary decision to define this vector as ST0. This could be 0ST. This could be S0T. Any variation of that. And more importantly, the 0 doesn't have to be there. This could be ST1 and just go completely above the origin, shifting it up. So just to conceptually wrap our heads around it, while it might be convenient to say that R2 could be a subspace of R3, it's too ambiguous to actually define it as a subspace. There's not enough of a constraint, and more specifically, this ST0 is the specific constraint to try and replicate what we want to say when we say R2 could be a subspace of R3, but it's not, because that plane could exist anywhere in, honestly, any particular orientation. But to show that H is a subspace of R3, well, let's look at the size of our vector. We have 3 spatial dimensions. We happen to pass through the origin. And as we can see, as this plane maps out, just assuming it goes to infinity as S and T are real, there's any combination of addition we could do, and we can scale this vector to any length we'd like to imagine, and we'd be able to contain it within this space, specifically this subspace of 3 dimensions, which is fun. I mean, it's kind of a trippy way to think about setting up geometries of space. But that's kind of the gist. One, it's not rigorous enough to say that just because you need 2 to get to 3, you can't say that R2 is inherently a subspace of R3. You have to put some kind of constraint on it, such as here we did with ST0. And it's specifically this constraint where the 0 would be that third entry in this particular vector that allows us to say that it contains a 0 vector and it meets all the criteria that would denote it as being a subspace of R3. Hopefully I didn't ramble on too long. I have everybody's attention still. Let's move on to a more fun one. Show that the set H of all points in R2 of the form 3s and 2 plus 5s is not a vector space by showing that it is not closed under scalar multiplication. Meaning we need to find a specific vector u in H and a scalar c that cu is not an H, which is a lot of verbiage, but is honestly not too crazy to think through if we get rid of some of the heavier math jargon. Effectively, it's already kind of told us our path to solution, our, disproving it with a contradiction is going to be with scalar multiplication. There's going to be some way to say that multiplying, if I construct this as a vector of 3s and then 2 plus 5s, if I pick some value of s and then multiply what that matrix would be by some number, so whatever, pick an arbitrary s, let's say s is equal to 1. So my matrix would take the form of 3, because 3 times 1 would be 3, and 7, where 5 times 1 would be 5 plus 2 would give us 7. And there has to be some scalar that I can multiply that vector 3, 7 by that kind of disproves this initial or contradicts this initial setup for the vector in R2 that we're trying to say is contained, and thus makes it not a vector space, because for it to be a vector space, I have to be able to add vectors together and have it stay within that vector space, and I have to be able to scale them or multiply them by some constant, and it has to stay within that bound. And unfortunately, for this vector, that's not going to be the case. So let's continue with the initial setup we went with. So let's say s is equal to 1. That means I have a vector in the form of 3 and 7. Let's scale that by 2. So now 2 times my vector of 3, 7 gives me an entry of 6 and 14 is my new scaled vector. Now, if we kind of backtrack through some of the math here, if I know that 6 is equal to 3s, then I can figure out what s should be. S should be 2. Now, if I plug 2 into here, that's where we start to encounter kind of a problem, because 2 times 5 is going to get 10 plus 2 is equal to 12. However, with what we just did, where we said s is equal to 1 and we scaled it by 2, we actually got our second entry of the vector to be 14. And it's that inconsistency between those second entries that pretty much sums up what the question's trying to have us do, which is find some way of showing that it's not closed under scalar multiplication. If it was closed under scalar multiplication, I wouldn't be noticing an inconsistency. I'd be able to pick an s, pick something to multiply both entries of the vector by, and I'd have no problem if I wanted to backtrack it and, sort of undo the algebra. But unfortunately, in this instance, because this plus 2 doesn't really go along for the ride as we kind of scale this variable up, there's going to always be some kind of a wobble between those values. It's going to get weirder as s gets larger. But we don't even really have to worry for numbers that big because we've already, again, at a very simplistic level of an S value of 1 and a scalar of 2, found that we already have an inconsistency. And that inconsistency means that we're not operating within a vector space. That's pretty fun, right? I think so. Oh boy. All right. So before we get into this, let's look at what our A matrix is, which, spoiler, it's a lot of numbers. And then we have two different vectors. And looking at this, it's probably beneficial to take in the geometry first. So the vector U is a 4x1 matrix, or it's a 4D vector. And V is a 3x1. And if we match that up to A, we notice that I have enough columns to go with columns going across an A to match up with the number of entries going down in U. And I also have enough rows in A that I have in V. This is going to come up to play as a factor as we start to answer these questions, because we're going to try and figure out what vectors fit into what spots as far as the null of A, or the null space of A, and the column space of A. But before we get into trying to talk through that, let's look at some definitions as I shuffle through some slides. So a null space is effectively going to be some X, or some vector X, that when I multiply it with A, it goes to 0, which, if we remember from checking for linear independence, we have our lovely AX equals 0. And to read through this definition, the null space of an M by N matrix A, shorthand null A, is a set of all solutions of the homogeneous equation AX equals 0. And in set notation, we're going to say null A is some X where X is in Rn, and we're going to take that in, that Rn is going to be the number of columns of our initial matrix A, such that if I multiply my vector X or V or U, whatever we want to call it, but we'll generalize it to X, that A times X is going to be 0. And the way to kind of interpret that is there's a solution set that's specific to this. Very big verbs here. That's specific to this A times X. It's going to get us to 0. So if we want to think about this as a space where a vector space would be a space where vectors can be added and multiplied together, subspaces have some tighter constraints within that grander vector space. The null space is this particular vector space that exists for the solutions, to kind of oversimplify the idea. So we're going to take a peek real quick, because again, the geometry is the thing to pay attention to here. So if I have some matrix A where it has n number of columns, I can qualify something to potentially be the null space of A, or within the null space of A, if that vector exists in that nth dimension. So if we pop back in here to our equation, I have an m by n, so I have a 3x4. So I'm looking for a vector that exists in R4, or fourth dimension. And we'll zoom in because that looks nicer. Going through these, I can immediately disqualify V because it only goes to 3. Whereas U goes to 4. And if you don't want to think of this conceptually in terms of math concepts where you're generalizing AX equals 0, you just have to know that you have to have two vectors in general, or two matrices that can be multiplied by each other to get to 0. And going through even just the fundamentals of matrix multiplication, I cannot multiply A by vector V. It just, it's not really, going to happen like that. But I can multiply this. Now the trick here, and as you notice, just even going off this geometry, we've already kind of ruled out some options. So you could be within the null of A. That's a possibility. V, however, cannot be within the null of A because it has to be in the nth dimension dictated by that matrix A. And in this instance, the nth dimension is going to be the fourth dimension. This is only in R3. So we're missing a dimension there. The other constraint, as we'll double back to this bit right here, is that when I multiply the matrix A by X, that has to equal 0. So if you enjoy keeping some numbers in your head like I do, we'll check this out real quick. So multiplying this out, I have 2 times 3, which should get me 6. 4 times -2, which is going to be -8. Remember, we're adding these all together. So 6 minus 8 gets me to -2. Great. And then -2 times -1 gets me +2. So -2 plus 2 gets me to 0. And then 1 times 0 is 0. So in my solution, I have a 0 in the first entry, which is great. That's exactly what we want to see if we're trying to see if this is in fact within the null. Now let's try our second row multiplying that out. So -2 times 3 gets me -6. -5 times -2 is +10. So that puts me up to +4, where we're at right there. Plus -1 times 7, which is going to be subtracting 7, which puts me at -3. And unfortunately, this 3 times 0 gets me to 0. So my solution, which I want to be all zeros, contains a non-zero. And if we're going through our reference material, if I can find it real quick, we can actually see here that as we do the math out, this is what we get. We get a 0, a -3, and a 3 for our solution vector, which unfortunately isn't 0. So from that, we can conclude that vector u, although it meets the geometry requirement for what we're looking for to determine whether or not it's in the null of A, does not actually satisfy our condition that when A is multiplied with U, it has to equal 0. Doesn't happen, so we can conclude that it is not within the null of A. Now, let's talk a little bit about column spaces. A column space of an m by n matrix A is all of the mth dimension if and only if the equation A times X equals B has a solution for each B in Rm. Again, a lot of math terminology there, or kind of generalizations. The main thing, again, picking up on the geometry, is now we're going off the number of rows. Or rather, in another way to think of it, the dimension, when I'm thinking of the dimensions of my column space, these are my columns going down. So I have 2, -2, 3. I have 4, -5, 7. I have -2, 7, -8, 1, 3, and 6. Now, I'm not reading horizontally, I'm reading vertically, and each one of those goes down a total of 3, which is why we're talking about the mth dimension. So going through and just looking at our vectors u and v again, it at least needs to be, it has to match that m value. So in this case, my m value is 3 because it's a 3 by 4 matrix and m by n. So my vector needs to match that if I want to consider it to be viable to be in the column of A, or the column space of A. So U is unfortunately in the fourth dimension, nth, in this particular instance, because it's a 3 by 4. Whereas V stands a good chance of being within the column, just based on the geometry here. Is again the main thing we want to look at. And just kind of going through, again, we haven't done a ton of math outside of a little bit of vector multiplication just to really conclude the null here, but we've already gone through just looking at the shapes of these vectors in this matrix 3/4 of this question, which is really cool to think about. I mean, just the spaces get really interesting the more you kind of analyze this. So let's take a peek down here. Again, we're going to multiply a times the vector that we are checking, which again, we're going to multiply a times v, and we're going to see if we get unique solutions, unique-ish. I just want to make sure that I have at least m number of pivots, because if I get down row reducing and I find out that, yeah, these, I have a pivot here and I have a pivot here, and this is all zeros at the bottom, we've got some dependence issues there. And that raises some problems, at least in terms if we want to conclude that this is in the column space of A. But luckily, people who wrote this book did us all a favor and saved us a little bit of laborious math. But as we get down here, we can notice that it is consistent. I have some number of pivots. I have 3 pivots in this instance. And since we have a consistent solution from multiplying A times V, meaning I have B's that are satisfied, or I have answers over in here that can be satisfied through that multiplication, I can conclude with that fact, and also taking in the geometry of V in terms of the, I'm going to try not to say too much word jumble there, but because it's a 3-dimensional vector, which happens to match the number of rows of that A matrix, the geometry checks out. And because we have a consistent solution to our row reduced setup here, it's a match made in heaven, really. We can conclude that it's a column space. And just again, for consistency's sake, to get through the second part of this, it can't be the null, because for it to be the null, it would have to match the n number of dimensions in A, which would be 4. And this is only a 3-dimensional vector. So a lot of fun talking about spaces in geometry, a lot of really interesting abstract concepts. I appreciate your patience sticking it out with me as we work through this, but a lot of really interesting stuff. So I thank you for tuning in. Hope to see you in the next one. Take care of yourself.